When we were learning about electric fields, first we learned about the electric field from a point charge. Then we learned about the electric field from multiple point charges. Then we learned about using each little tiny chunk of a charge distribution and treating it like a point charge and adding up all the contributions to find the electric field. Well, we did all of those same things with electric potential. Found the electric potential from a point charge, found the electric potential from multiple point charges, and then in the last video, we treated every little tiny element of a continuous charge distribution like a point charge and added up all the contributions to find the potential near a charge distribution. It was a little easier though because electric potential is a scalar, not a vector, so we didn't have to worry about components with electric potential. What did we do next with electric field? We said that if we have certain very special symmetries, right, spherical symmetry, cylindrical symmetry, or infinite sheets, we could use Gauss's law to very quickly and easily find the electric field. So now we're going to say, well, if we know the electric field, maybe we can find the electric potential using a different method. And that's what we're going to do now. This is an equation we're going to become very familiar with. The change in electric potential is equal to negative the integral of E dot ds. So if we know the electric field in some region of space, we can just integrate E dot ds between 2 points and figure out the potential difference between those 2 points. When do we have the electric field? Well, when we have nice symmetry like spherical, cylindrical, or infinite sheets, we can find the electric field very easily using Gauss's law. So if we see one of those geometries and the problem is asking for a potential difference, oftentimes the easiest thing to do is to use Gauss's law to first find the electric field, and then use this equation to integrate the electric field between 2 points and get the potential difference. Sometimes it's just easiest to do a problem and see how you would apply a certain procedure. We're going to find the electric potential everywhere given a cylindrical charge distribution. Our cylinder is a solid, conductive cylinder, infinitely long, radius r, charge per unit length lambda, and we'll just make it a positive number. And we have to be given where the potential is 0, because we would only be able to find delta V using our equation. So we have to start at a known potential, and then we can find the potential everywhere else. First thing we need to do, we look at this, and we say, wow, integrating over this charge distribution would be really tricky. Adding up all the contributions from every little dq over the surface of a cylinder to some location, that's a tough thing to set up. But finding its electric field everywhere and then integrating that between 2 points looks a little more doable. So we'll do that. First thing we want to do is find the electric field everywhere. We'll start inside the conductive cylinder. We know our conductive cylinder has positive charge over its surface. Because it's a conductive cylinder, any excess charge it has repels itself and ends up on the outermost surface. So inside of this cylinder, I know my electric field has to be 0. Now we'll find the electric field outside of the cylinder using Gauss's law. I've drawn my red Gaussian surface. It's a cylinder with the axis along the axis of my conductive cylinder that's charged, so it matches the symmetry of the problem. Now I just apply Gauss's law to get the electric field. The integral over my entire Gaussian surface can be broken up into three integrals because my Gaussian surface is a cylinder. It has a top, it has a side, and it has a bottom. The integral over the top and the bottom are zero. There is no flux through those surfaces. The electric field skims along those surfaces parallel to them. It does not penetrate those surfaces. Those are zero. The integral over the side gives me E times the area of the side. And the area of a side of a cylinder is 2 pi r, right, the circumference of the circle if you're looking down at the end, times the height, where this is the height. How much charge is enclosed inside of my Gaussian cylinder? That's all the stuff in here, all that charge. So it's the height h multiplied by lambda, the charge per unit length on my cylinder. The h's cancel, and the electric field drops off as 1 over r as I move away from the cylinder. Now we know the electric field everywhere. We know it from 0 to capital R, the radius of our cylinder. It's 0 in that region. And we know it from capital R to infinity. It's given by this equation. This equation will tell me delta V by integrating the electric field between 2 points. So I always want to start where I know what the electric potential is. And I know in this problem the electric potential is 0 at the radius of the cylinder. So I'm going to start there. And then I'm going to work my way out to infinity, and I'm going to work my way in to 0. We're going to start on the surface of our cylinder and go out from there first, and then we'll go back and start at the surface and go into the other region. So there's our initial location, that's our starting point. This would be our initial, and we're going to go out to just any arbitrary point out here. And we're going to use our equation. The change in potential is minus the integral of E dot ds. Now I'm going to try to get my minus signs right, and in the end I'll just fix it if I'm wrong. So let's see what we get. What is the electric field? Well, I just found that using Gauss's law. There's my electric field. ds in this case is just dr, right? We're moving radially in and out in a cylindrical coordinate system. And the dot product is the angle, the cosine of the angle we get when we put the tails together, ds and our electric field. Our electric field, we know, points out, and dr points out. So we're going to have a cosine of 0 degrees here. And our limits of integration are from our initial to our final, always from the smaller number to the bigger number when you're doing limits of integration. Delta V is going to be our final potential minus our initial potential. We know our initial potential is 0. That's where we're starting. So on the left side of our equation, we're going to have a V final. And what does V final have to be? Positive or negative? let's take a look at our situation. Our electric field, because this is a positively charged cylinder, our electric field points outward. We're moving outward. We're moving in the direction of the electric field, so we have to be moving to a position of lower electric potential. The electric field always points toward lower electric potential. So our final potential has to be less than our initial. And our initial is 0. What's less than 0? A negative number. So our final potential must be negative. Now we just need to make sure the right side of our equation gives us a negative number when all is said and done. So if it doesn't, we'll fix it, we'll make it negative. But if we get all of our signs right and our dot products and our limits and everything is just right, it'll give us the proper sign. Lambda over 2 pi epsilon naught, those come out, those are constants. I have the integral of 1 over r dr. And that's just the natural log of r. If you remember your log properties, the natural log of r final minus the natural log of r initial is just the natural log of r final over r initial. Our constants are positive. The natural log of r final over r initial is positive because r final is bigger than r initial. The natural log of a number greater than 1 is positive. And so this minus sign over here is needed to make this whole thing negative. So it looks like we got our signs correct. The left side of our equation is v final. It has to be negative. The right side of our equation has to be negative. Always stop at this point and check your signs. All right, we can move on. Okay, so what is our initial? That's just the radius of our cylinder. So I've got my v final is going to equal negative lambda over 2 pi epsilon naught. And I'm just going to call it v at any r. V at any r is equal to this value, and r can be anything from capital R to infinity. Now let's find the electric potential inside of our cylinder. So we're going to start on the surface of our cylinder and work our way in to some other location. So this is going to be our final. This is our initial. And we say delta V minus the integral of E dot ds. Delta V is minus the integral of E dot ds. This is V final minus V initial. And the right side of the equation is 0. Let's plug in what we know about our electric field. Our electric field is 0 in this region. So the right side of our equation is 0. The change in potential has to be 0. Let's see what our potential has to be. It has to be whatever it is on the surface of the cylinder. It cannot change. It has to be constant. On the surface of the cylinder, it happens to be 0 in this case. So V final is 0. V at any location inside of our cylinder is 0. When the electric field is 0, delta V has to be 0, which means V has to be constant. In this case, it happened to be, the constant happens to be 0, but it doesn't have to be 0. It has to be whatever it is on the surface. It has to stay the same as it is on the surface.